Hi, I'm going to read an article I wrote on Quora concerning the Collatz conjecture. So I've been writing articles about this conjecture for 4 years, and I've accumulated a lot of ideas, but actually my original ones were pretty accurate, and I haven't changed my mind about them. So this article covers a lot of those ideas, not all of them. So I write this as from a computational point of view, not as a mathematician would think about it. Uh, so the question was, what does solving the Collatz conjecture mean? So my answer is first just to say exactly what the conjecture is asking, and then to address the two main propositions in the conjecture as I understand them to be solvable, using mainly logical and computational arguments. So this is my answer. This is a good question because there seems to be some disagreement whether the conjecture is one problem or two. Here's how I would say it if it was split down the middle. Prove the following two propositions are false for the 3x plus 1 function. And by the way, as you know, the conjecture is also called a 3x plus 1 problem, and it's called that because it represents a function in which you multiply any number by 3 and add 1, any odd number by 3 and add 1, which gives you an even number, and then you divide it until you get a smaller odd number, and you continue in this way until you reach 1. It is pretty facile. I can think of some fourth grade number riddles which work basically the same way and end in 1. What I will say is this one has captured the popular imagination, and for reasons that are not entirely explainable, and it's captured the attention of mathematicians because they see two possible problems with it. So the two reasons that might perturb the return to 1 from any odd number, or any even number as well. In case of an even number, you would, if starting with an even number, you would have it until you got to an odd number, and you would be in the same cycle, same function. And I would actually say the way the function is described is totally misleading and, childish in a sense. So I'm going to get to that later on as well. But so the two propositions which you need to prove false are that there are sequences that loop and that there are sequences that diverge from 1 perpetually, meaning to infinity. So solving the conjecture as it stands would be proving both those propositions are false. Proving one or the other to be false would be half a solution if it turns out that they are different or not fully aligned questions. Each proposition may require a separate proof, and one or both propositions may be shown to be undecidable. And undecidable is a conclusion to the conjecture. It would, if provably undecidable, that would prove that it cannot be true or false. It could be true or false, but it's undecidable which one it is. That is an acceptable end to the conjecture. So I just want to underline something, that without those perturbations, without those false propositions, every single odd number subject to 3x plus 1 will end in 1. And this is elementary arithmetic. There can be no question about this, and there is no need for a separate proof of this. It's true by definition according to the rules of the game if those two propositions are false. So that's just a diagram of how I would imagine on the left infinity occurring, the proposition of infinity, and on the right the proposition of looping. So with respect to the propositions of infinity, it's not necessary that the sequence even goes close to 1. I'm showing it there like a failed orbit, but it could be anywhere in the infinity of numbers that it strays away and doesn't hit 1. The other one, the loop, could be of any size, any inconceivable size. So again, very, very hard to prove. So it's possible that both propositions are undecidable. That is really a realistic opinion based on the standards of number theory and of mathematicians. But from my perspective, it's extremely hard to imagine what infinite divergence means. I mean, obviously, it would defy the law of probability beyond imagination. It's like asking a coin toss to go on until an infinite number of times, and that infinity would be contained in a larger infinity, which is the notion of sets and infinities that was put forth by Cantor, Georg Cantor. So, this is beyond any imagining. So again, the possibility of defying probability, as in Goldbach's conjecture, probably would mean nothing to a proof. Wouldn't mean nothing to a proof in the domain of number theory. That's not the point of number theory. Number theory doesn't care about probability. It cares about a deterministic proof that would be true through infinity, and infinity never ends. Even for the natural numbers, of course, which are countable, it never ends. Now, I have what I think is a very strong logical objection to this when you recast the question this way, because you're asking for an infinity within an infinity, and the question is actually, can there be an infinity within an infinity in this particular case? Because both situations are involving the natural numbers. So can you prove that for the infinity of natural numbers, there can be a sequence of natural numbers that is infinitely divergent? Now, is that even a possibility? Like, normally when we talk about different sets of infinity, we are talking about different kinds of numbers, such as the real numbers versus the natural numbers, and it's extremely easy to understand why the infinity of real numbers is greater than the infinity of natural numbers. But here we're just talking about the natural numbers. So it seems to me that this is unprovable, or provably undecidable, much more provably undecidable. And it's also worth thinking about the fact that in an infinitely divergent sequence, every number, without exception, and for infinity, would have to be in a different set of integers than every number in a convergent sequence. So these sets could have no intersection. No number could be in both a convergent and a divergent sequence. A divergent in the sense of diverging into infinity. And then in contrast to that, a converging sequence, that is every known sequence that has been observed up to 10 to the 48, or maybe it's 78, I forget, is infinitely divergent from 1. So we can talk about divergence in that sense, starting from 1 and diverging to infinity. Now, that is the truth for every sequence we know. So by that I mean 1 is not just the end point, but also the starting point of every sequence. And every sequence is infinitely extensible, which I explain further along. So I put forth the idea that if there existed a function that output every odd number as a member of a converging sequence, would that not account for every sequence? And would that not mean that all sequences were infinitely divergent? such a function infinitely divergent from 1, and I'm getting muddled here, and none could be infinitely divergent. Such a function does exist, I maintain, and I will show you what it is, and that would seem dispositive, meaning it sort of settles the question. And if it settled the question at that level, then the undecidability problem would actually go away, which would be very, very nice. So at this point, you can stop the video if you wish, unless you're interested in my computational opinion of the conjecture. And my opinion is not a very high one. That is, computationally, it's hard to see what all the fuss is about. So I get this sentiment from a lot of engineers who have looked at it, at the 3x plus 1 problem, and really the reaction is, well, why did number theorists become preoccupied with this little algorithm? Because that's what it is. It's a function, it's an algorithm, it can be represented so easily, the results can be produced so quickly. What is going on here? What is this obsession? It seems like it's a Rorschach test for mathematicians, and that's why they're really getting stuck on it. And they're warned not to waste time on it because there is no solution to it, given current mathematical tools. However, it does seem to enthrall some portion of the public, to which I belong, who are just a tiny bit math literate. Now, there was a recent Veritasium episode, and probably know about those on YouTube. They're followed by a huge number of fans. He gets, I think his name is David Muller or Robert Muller. He gets like 5 million views per episode. And he has an amazing talent for making this stuff entertaining, including the 3x plus 1 problem. So, continuing, and I'll consider the infinity problem first. So I want to substantiate my previous statement that every known sequence is infinitely divergent from 1. So there is a way to prove this, and it's kind of neat. It almost reminds me, without sounding vain, of the Euclidean proof of the infinity of primes, except it's even simpler than that. So I'm going to address a well-known number 27, and it's well-known because it has a big or long stopping time for a small number, and it really makes an impression on people when they see this number for the first time. How long the sequence is. They're just surprised by how long the sequence is, and it's so out of line with the other small numbers. So, but I'm saying that this sequence can easily be extended simply by multiplying by 4 and adding 1. And every time you do this, you're creating a longer sequence. So you're multiplying it by 4 and you're adding 1. You're making a longer sequence. The sequence is only one odd number longer. However, that will continue till infinity, and that is deterministic. It will continue till infinity. Each multiplication by 4 and addition by 1, and I see I'm missing my plus 1s on those two, will create a longer sequence, longer by 1 odd 1, and I think 2 even numbers. But we're not going to talk about the even numbers much because they're a waste of time. Now, your objection, I don't know about yours, but an objection I will find is that, well, 27 is a standalone number. It does not appear in the same sequence as 109 or 437 or 1749. Now, this is true if we consider the conventional form of sequences, which is even and odd numbers. So I present this here, right and wrong, using the verbose even odd form of the sequence to illustrate it. There are actually 2 merging branches, 109, 328, 164, and 27, 82. So both these sequences, the one from 109 and the one from 27, converge on 82 and then 41. Odd only, just 41. Odd even, no 27. Straight from 164 to 82, no 27. So I will explain a little bit more about how branches merge in a little bit. Now, the obvious thing has to be said. If one step is the same, all the steps that follow must be the same. And that goes for the even numbers as well as the odd. They are the same sequence as soon as that happens. So it's equally accurate to say the odd-only sequence is 109 to 27 to 41, because 27 is hidden by an artifact of 3x plus 1. And there is a way to correct this by using a superset function, which I will demonstrate, or at least show to you. And that fixes the problem by including the numbers that are evenly divisible by 3. By definition, 3x plus 1 must exclude every number evenly divisible by 3. So the superset function, in my opinion, is proof positive that every odd number is a member of the convergent sequence. Computationally, it must be, but mathematicians see differently. It's merely that the halving function of 3x plus 1 generates 109 to 41, and what I will call the quartering operation of the superset function generates 109 to 27 to 41. So with a computational mindset, I'll switch to the central question of whether or not there can be infinite sequences that do not begin with 1, because ending with 1 and beginning with 1 is actually the same thing, just looking at the same sequence, one forward or reverse. So the answer again is no, because the growth operation cannot continue indefinitely arithmetically. The 3x plus 1 problem concerns congruence-based operations, and that's something else that you won't hear about when you hear about the Collatz conjecture and the 3x plus 1 problem. I've just got to break for a quick drink. As a sequence of numbers is generated, the congruence of those numbers changes, and with each change, the output operation changes. The congruence that produces the expansion operation or operator is followed by a congruence that produces a reduction operation or operator, and these occur over and over again in tandem. And there's actually 3 such operations: 1, a growth operation, and 2, a reduction operation. So putting aside what you may believe is the Collatz function, I will just state that the expanding operation is this. It is not a recursive operation, with these divisions by 2. It's a straightforward division and multiplication operation. So you might not get this, but it doesn't really matter. If m plus 1 is divisible by 4, so that means it's congruent with 0 mod 4. So that's the congruence. It's congruent with 0 mod 4, meaning it's evenly divisible by 4, and multiply by 1.5, and then subtract 1. So you're talking about an odd n, and we'll look at a table a little bit further down, but an odd n plus 1 makes it even. Then you can apply the congruence and multiply and subtract 1 to make it odd again. And there are 2 reducing operations. If m minus 1 is divisible by 8, multiply by 0.75 and add 1. So you'll notice that I'm subtracting 1 from n, not adding it this time. And then I'm attempting to divide by 8. So it's m minus 1 is congruent 0 mod 8. Is evenly divisible by 8. Then you do the multiplication operation and add 1 to make it even again. And the final operation is if neither of those two cases apply, simply multiply n minus 1 by 0.25. That's the quartering operation. Now, that last case corresponds with a congruence of 2, a congruence of 0 mod 2. So these are the three cases, but they have to be taken in order. Otherwise, the last one would cover all cases. They have to be taken in order. Now, the interesting thing about these three operations is you can actually lose the congruence classes and test all three. And every single time, only one will produce a whole number, a whole odd number. Only one of those three operations for every n will produce a whole odd number, and that is the next step. So although the congruence is helpful and is operating in the simplified case, you can see sort of the elemental quality of this, and that these three operations are the heart of the problem. Multiplying by 1.5, multiplying by 0.75, a reducing operation, and multiplying by 0.25, a quartering operation. So we can call these three operations A, B, and C, respectively. The first operation occurs twice as frequently as each of the second and third operations, so the ratio is 2 to 1 to 1. Now, I can show that again on the table why that's true when we're going to get to a table further down. So if we do the arithmetic, 1.5 times 1.5 times 0.75 times 0.25, we do come out with this number, which I don't know if it's meaningful or not, 0.42, which certainly implies that all things being equal, every sequence will get smaller. But that's just really a crude approximation, and I think we can be more precise than that. So what this does not take into account is that each operation can be repeated several times, but deterministically, not an indefinite number of times. It's not like tossing a coin. That's very, very important. It's not like tossing a coin. And I'm going to show why in a minute. Because I think that when number theorists contemplate infinity, there could be a case of an infinite but smaller infinity of the coin toss, always producing the same result. That's the nature of Cantor's infinity. You may not be able to disprove that possibility for a coin toss, but you definitely can for the Collatz conjecture, and I'll explain why here. So by taking the odd numbers of a sequence and adding 1, we can see factors of 2, how factors of 2 behave. I'm not talking about powers of 2, which is a naive solution to part of to some sequences, to a limited set of sequences. I'm talking about how factors of 2 behave. And this is very, very convenient and interesting, that when you add 1 to any odd number in a sequence, you get a lot of factors of 2, it seems. Factors of 3, factors of 2. I'm not going to put my money on this because I maintain every odd number can be in a sequence. But it's interesting in some cases, and this little snippet is from 27, from the sequence of 27. So while it may not be immediately obvious why, this determines when the congruence of the next step must change. So what we have here is you'll see that the factors of 2 are diminishing as the odd numbers get bigger. So we're applying over and over again congruence A operation, and this does occur in 27, but you get the same congruence operation, the multiplication by 1.5, up to 5 times. And that's what accounts for the length of the sequence, because you get these relatively big numbers. But notice that the number of factors of 2 is decreasing with each multiplication by 1.5, and that's not surprising because you could only maintain those factors of 2 or increase them if you were doubling the number, but you cannot do that in the Collatz sequences. You could only multiply by 1.5. So this means that factors of 3 begin to replace factors of 2. So the factors of 2 must always exhaust themselves, and you cannot have less than 2. So I think I've explained that sufficiently. Now, the same thing actually happens for congruence B and congruence C, operation B, operation C, but they cannot continue indefinitely. At some point, and it's after a few iterations they have to switch to another congruence. Now, the only weakness in this argument is, although we can say the expansion operation is always self-limiting, one could still imagine a kind of valley, plateau, mountain scenario where the valleys and plateaus are getting a little bit higher after each mountain. Again, it's ludicrous to imagine this could go on for very long, but from a point of view of number theory, anything can happen on the way to infinity. So here we're coming to the functions that I propose, and I've essentially described the first function. So I've just put it in the form that a mathematician might put it in. So we got n plus 1 multiplied by 3 over 2 plus 1 if n plus 1 is congruent with 0 mod 4. And then n minus 1 multiplied by 3/4 minus 1. I think I might have made a mistake there. If n minus 1 is congruent with 0 mod 8. And finally, n minus 1 multiplied by 4 in the alternative case, which is really mod 2. But as I say, the up-through operations need to be taken in order. So this, obviously, every output is then put into the function again as an input. And there is a divergent form of this function, which is mirror image of the convergent form. In other words, if you choose a number like 11 and run it out 100 times or 1,000 times, if you take that final result and put it into the divergent function, into the divergent function, so let me just clarify that. So we start with 11 and we run it out 1,000 iterations using the divergent function. Then if we take that number and put it into the convergent function, it's going to go back to that original 11 or whatever number you started from. It's going to actually replicate every number in the sequence. Once it gets to 11, then it will continue to 1 or whatever number. This is actually a form of idempotence, which means that you can run the numbers through a function either direction and nothing changes. It's, they are mirrors of each other. So I think I've covered this, and there's an example of starting at 1179, getting to 21, 20, 11, 11, and then going back the other way. And I think I've got the forward and the reverse the wrong way around there. So they taking the functions together, they are idempotent. So I previously mentioned a function that outputs every odd number. Well, the above functions do. they output the numbers that are missing from the Collatz Syracuse functions. And by the way, the Syracuse function is just an odd-only version of the Collatz function. They output the numbers that are missing from those, and those are the ones that are evenly divisible by 3. So one can think of these functions as being superset functions. And what's true for the superset is true for the original set, the 3x plus 1 set. I don't know if that has to be another proof, probably a lemma, but it's definitely true. So here we get to why are there no sequences for loop. So I think I've actually completed the first half of the article and the longer half of the article, so don't give up yet. That was the one concerning infinity. So now we're going to get to the question of why there are no sequences for loop. So before I get to this, you need to understand how sequences merge, because one of the first ideas I had was that looping sequences came out of merging sequences, and it turns out they're completely different and there's actually no connection. So there's nothing, for 3x plus 1, there is nothing discernibly to do with looping that is related to merging. And by the way, there's no branching. There's only, unless you're going in the reverse direction, it's merging. So every sequence that converges on 1 merges with other sequences repeatedly, actually, to the penultimate number, the step before 1, which may be 5 in the odd sequence. So it happens when 2 operations produce the same result, and this is going to happen over and over again. For example, 1109 and 1137 converge on 13. Now, how is this? Well, it's not really important how they get to 17 and 53. What's important is how 17 and 53 both converge to 13. So it's because of the 2 reducing operations I showed before. So 17, if m minus 1 is divisible by 8, multiply by 0.75 and add 1. So 17 minus 1 is 16. It's divisible by 8. Remember, the first operation, the growth operation, you have to add 1 to n. So it couldn't be divisible by 8. It couldn't be divisible by 4. So that means the second operation comes into play. So 17 minus 1 divided by 8 equals 2. So that's a congruence of mod 0. So you multiply 16 by 0.75, which is 12. And then you add 1, which is 13. So we have 13 there. And then above the line, and then, and then below the line for 53, we simply make that 52 and divide by 0.25, or multiply by 0.25, and we get 13 again. So there is a merge. Now, it's actually easier to understand this in a table, and you can really think about this, the Collatz conjecture, as just being a table of inputs and outputs. So the middle empty column is the dividing line between the inputs and the outputs. And the first column is A, the second column is B, and the third column is C in the inputs. And so you can see in the A column, you have every other odd number. Not all of them, every other odd number, 15, 19, 23. In the middle column, you have each odd number separated by 8, if I'm not mistaken. So we have separated by 4 in the first column, separated by 8 in the second column, and in the third column, we have again separated by 8, but it's a different sequence. It's starting on a first number is different, and I haven't started from 1. I just wanted to show a little bit of it. So in the outputs, I think the thing that's worth noting the most is that in the third column, every odd number is represented. Every odd number is represented. But because the gaps between them in the table are, it's every fourth row in the table, say we get down to 27, we're really a long way down, and we got quite big numbers. We're dealing with the inputs and outputs, crudely put. But so if you see here, you'll see why 17 is input 17 becomes output 13, and input 53 becomes output 13. Now, this will never produce a loop, this feature, the two numbers output the same number. And really, it's actually, well, for me, it was quite hard to get past this idea that that's what looping was about. And it's not. So let me just move on and say, so this is really getting to the question of looping and how it's different. So the way I see to prove 3x plus 1 sequences cannot loop, except for this very so-called trivial case, but it's also a very important case because it demonstrates how 1 is different. With 1, we get this sequence for the even odd numbers, 1, 4, 2, 1. And of course, for the odd numbers, it's just 1, input 1, output 1. We don't care about the 4 and the 2. So we need to look at counterexamples, sequences generated by 3x plus n, where n is greater than 1. And from my own investigations, it's easy to find loops in these cases where n is greater than 1. Actually, probably where n is greater than 3. So I think the properties of loops are poorly understood. I haven't seen mathematicians define them clearly or at all. They're looking for them. They think might be out there. They came up with some huge number where loops could possibly be for 3x plus 1. I can't remember what that is, but it's some region far out on the way to infinity. So I define a loop as a static collection of numbers whose common differences sum to 0. Nothing else. Nothing is going on. They're not spinning around. They're not merging and branching. It's just a static collection of numbers whose common differences sum to 0. You can think of a loop as a small set with a collection of these numbers. It doesn't matter what order you take them in, their common differences sum to 0. So this might seem like a strange way to define loops, but the arithmetic is simple. They cannot exist without the common differences summing to 0. All 3x plus n functions have what I will call an equilibrium point of n. Now that's pretty simple. Thus, for 3x plus 17, it's 17. It means that the trivial loop always occurs at n, such as input 11, output 11, or input 13, output 13, where 11 or 13 is n. The sequence halts at the number in the trivial loop. Now I'm reading this, I'm finding all kinds of typos and errors. The sequence halts at the number in the trivial loop. Now, obviously this doesn't matter to 3x plus 1 because the sequence halts only in the trivial loop of 1. That's what I maintain. That's why there are no other loops. So my observation from looking at complex loops generated by 3x plus 1 sequences where n is greater than 1, and these are easy to find as I mentioned, are that they too are related to the equilibrium points. Since negative numbers are not possible in the Collatz conjecture, 1 is not a true equilibrium point. So there cannot be a complex loop around 1. For n equals 7, or n equals 11, or n equals 17, and so on, there is such a possibility. So I will just provide the example of 17. So here is a loop for 3x plus 17 that started with n equals 27, or started with the first number of the sequence as 27, and it turns into a loop on 11, which I think is just a few steps on from 27 in when the addend 17 is used. So you hear a lot about people asking about, well, what if 3x were 4x or 7x or 11x or whatever? No. That is totally irrelevant to the 3x plus 1 conjecture. And by the way, those will produce infinite divergent sequences. We need to look at the addends, and here we're looking at 17, and a loop does begin on 11. Except the notion of beginning a loop is oxymoronic, tautology, whatever. Once in the loop can begin with any number of the set of numbers in the loop, and it's not even beginning with them because, as I say, they're a static collection. But you can graph it like this. This is the order in which the numbers appear in the conjecture, in the sequence. And I've put the numbers under the graph so you can see what they are. It begins with 11, ends with 11. It's asymmetrical. It has no qualities that would suggest merging or branching or symmetry. The only thing that defines it as a loop is it sums the common differences of these numbers sum to 0. And I just mentioned that I should have illustrated this. So what I mean by common differences would be 25 minus 11, 23 minus 25, 43 minus 23. So you've got odd and even. Sorry, you've got positive and negative numbers. So that's why it sums to 0. And believe me, it does. I should have illustrated it, but I didn't. And interestingly, if you apply this notion of common differences to 3x plus 1 sequences, you always end up with 1. And I think there's a pretty simple reason for that, but it was intriguing when I first noticed it. So I want to suggest why these loops occur for 3x plus m where n is greater than 1. And so, again, using the tabulation I used before, but squishing all the numbers just into 2 columns, you can see that 1717 is the trivial loop. There's no common difference. It's 0. But on either side of that, separated by 1 row, you have 11 to 25, which is plus 14, and you have 13 to minus 1, which is minus 14, so they cancel each other out. Similarly, you have 21 to 1, which is minus 20, and you have 23 to 43, that is plus 20, which cancel each other out. Now, I theorize that this is the reason you have loops, because of this symmetry. Without the pairs of inverse operations, the common differences in the example would not sum to 0. And that is the essential property of cyclicality. A set of integers, again, cannot cycle without the paired inverse operations. It's an observation, and I have no clue how to prove it. But I believe it's a necessary and sufficient reason for a loop, for a perpetual non-trivial cycle. So I also believe that these complex cycles actually always occur around the equilibrium. They don't occur far out in sequences. I haven't tested this extensively. I might be completely wrong. Now, we're right at the end now. So there is a dissimilar property for 3x plus 1, because 1 is the first positive integer. It cannot have symmetrical inverse operations less than it, because they're negative numbers. There is only one inverse pair. 1 is, in fact, a disequilibrium point. It's a disequilibrium point. You see there that, there's nothing less than 1. But you do have a failed you have one pair with the inverse property, but that's all you have. So that's, it's asymmetrical around zero. So, when I say, I don't know what I'm going to say. Further, you can tabulate that such pairs of inverse operations cannot exist elsewhere on the number line for 3x plus 1. In other words, if you think about that table before, you can see that no, they cannot be common differences, paired common differences that cancel each other out anywhere on the number line for 1. So again, that seems dispositive for the question of looping. So that's the end of my talk. And thank you for listening.